formally, it's very easy to write this in time, but I will actually be interested in effect of what happens average over all times. So at this point, I'll use a Laplace transform. We care about long times. So computing this rate just for one repeat usually won't be terribly useful. And the Laplace transform is just, you go from the present, and you might have to worry about the instantaneous moment because I'm on the border of my delta function at the instant. So I'll let go just a short time, and then off to infinity. So this is epsilon, strictly larger than 0 and positive, but arbitrarily small. Then the Laplace transform says trade in the time by its dual variable. So in quantum mechanics, this will be energy, but here it'll turn out to be decay rate, or it'll have interpretation of something that's decay per unit time is a typical interpretation. And then we look at our integral, and we only focus on the first part here, because that's where Dirac delta kicks in. It's time dependence. And we'll take a point on a cycle parameterized by time tau, because the time works as a parameter on this cycle. If I take seconds, it'll give me little dots around here. The cycle itself is parameterized by tau going from 0 to the length of the period. And I'm interested only in the parallel coordinate. What I'm interested in is the final point compared to the initial point. And I already know this will be only of interest if I get something at repeat of the period, and then I'll put time here. And if I write it this way, the contributions I'll get is only when the time is actually around this period. So I can write this as a sum over E minus S RTP. This will be exactly a delta function. R goes 1 to infinity. And then little integrals in time close to bracketing 0, because that's when t is 0 that picks up a thing. And I can take this to be minus epsilon to epsilon. This is kind of thing that will appear in my Laplace transform, but I also have to integrate over the parallel direction. I have to take a trace of this. So the object that is of interest to us, in addition to this Laplace transform, we also have to integrate over, because we are computing probability that point recurs over all initial conditions. So we have to start any place on the cycle. And at the moment, we'll just find contribution of parallel coordinate. Now, the way this formula stands at the moment is a little bit awkward, because we are computing something over delta function in length in a spatial coordinate, but we know that it's only going to pick up contribution when time satisfies the condition, periodicity condition. So what we want to do is we want to go from parameterization of this periodic orbit in terms of its length to parameterization in terms of time. That's easily done. You're just going over one period. delta tau. And the Jacobian that you pick up is actually the velocity in parallel direction, x, right? Because you have to compute dx prime over d tau. But that's actually just this velocity. So in terms of parameterization, this function puts me to the point which is whatever was the initial point time t later. So that's the same delta function as here, just written in terms of displacement, but we have taken tau explicitly out. Now this delta function is a function of time. It'll create a so-called Dirac cone. You'll have a contribution exactly here, and then exactly here, and then exactly here, and zero elsewhere. So that means is that I can write this as a sum of, again, r equals 1 to infinity, little integrals, what did I call them? Integral r. Where each of these integrals, rth repeat, is a time integral from minus epsilon to plus epsilon dt es minus. So I pull out explicitly this factor and I just look at small variation in t around it. This time is very small, so what I can do is I can do a Taylor expansion to estimate where am I in short time, but I know how to compute it. It's where am I exactly at plus RTP plus the derivative of this with respect of time, which is the velocity evaluated at the same point. By periodicity condition, this cancels, and we find that little integral in this neighborhood, this will, when it cancels, this will get a contribution only at t equals 0, so this will be 1. So this will be just the integral velocity evaluated, but by periodicity, velocity is the same. We come back every time, so this is just velocity at time tau. We are here at time tau times t. But this integral we know how to do. It's just the variable multiplied by something. So this is 1 over the velocity. Now I don't have to put absolute signs around the velocity because on a periodic orbit, velocity is strictly positive at all times. I move all the time. If it goes to 0, then it's not periodic orbit. It's a heteroclinic or homoclinic connection. So I'm guaranteed. So I don't need absolute signs. And that's this integral. It's very simple. And now I can put that integral back into this. And I remember that I had velocity here when I went from original spatial coordinate to time coordinates. So this Jacobian exactly cancels. This velocity has canceled. We've gotten rid of this delta function, so only thing we're integrating is over one period, d tau. So we just get a period, and then we pick up a contribution r equals 1 to infinity So this is how the longitudinal integral works when you have marginal eigenvalue. We had to evaluate it explicitly, but it turned out it was very trivial. This was explicit in a marginal direction. And we used Laplace transform to get rid of Dirac-Coombe. We had in real time, we have a very complicated graph. When we have infinitely many periodic orbits, there'll be lines every time a period of some orbit shows up. So if you try to plot it in time, there are very few short periodic orbits. But as you go further and further, this will get more and more complicated because each orbit will have all its repeats. And what you always do in that situation, you integrate over it. In this case, you do it by taking Laplace transform, and that smooths out all this stuff and gets you an answer. And it says that the weight of the orbit is kind of volume. Prime periodic orbit is its length, which, because we've used Laplace transform in time, the length will be really measured in time. So it's length times the transverse volume, which is very easy to integrate, so I won't do it here. In video, I've done it already before. Just for the Poincaré map, that one is easy to do. So if you add, I guess I can write the answer. What you will get is you'll get a contribution from each periodic orbit. Each one of them will have a volume whose length is Tp, but its neighborhood will depend on how unstable the orbit is. So if it's very unstable orbit, it'll have very small neighborhood. Neighborhood is defined as something that after one repeat is still, close by, hasn't gone off to infinity or far away. And obviously, going twice around, the neighborhood will have to be still smaller because you're unstable. So. And the mathematical statement will be that the first repeat, second repeat, etc., they have different weights, but in extremely simple way. Because this is in d dimension, there will be determinant. Because the function is x minus f of x, when you take a derivative, x will give you 1, and derivative of the function will give you Jacobian, that we know. Evaluate on periodic orbit, but if I go r times around, then it'll just multiply itself on the periodic orbit. And I will still inherit this weight here. And the way you think of it is, periodic orbit contributes, its neighborhood contributes to averages I'm computing, because state space is partitioned in neighborhoods. Each neighborhood is some kind of closed loop or sausage or tube whose length is the period of the orbit and whose thickness is inversely proportional to the product of 1 minus eigenvalues, stability eigenvalues. Now, if these numbers are larger than 1, it's dominated by multipliers. So, and they're exponentially expanding, because if I go twice around, I just get multiplier 2 times, 3 times to the nth power. So this thing tells you what the thickness is of the neighborhood. And what does this thing say? Well, you know, there should be some penalty for taking a long time to come back, because obviously they should contribute less to my process than things that come back very often. So that's the penalty. You know, it has this parameter which will turn out to be an eigenvalue evolution operator, and it will turn out for probability conservation case natural measure S will be exactly 0. And then this won't show up, but if I'm looking at something that decays in time, then longer and longer recurrences are penalized. So all this is intrinsic to periodic orbits because the multipliers are intrinsic. They don't care about coordinates or anything. The period is intrinsic. Anybody who computes same dynamical system should get same periodic orbits. And the weight of this thing is totally coordinate independent. It just will tell you how important the periodic orbit is. So that's why we evaluated this straight.